Hi, NA Physics, it's Mr. Neff. Today, let's talk conservation of energy. But before we do, how do you get warm in any room? I'll tell you about that at the end of the video. Now, look at this. I have two examples of work here, and I want you to calculate how much work is happening in each case. On the left, I have a basketball that's going up into the air, and so it is slowing down, and so that gives you a hint about the sign of the work. Basketball is going up into the air. I have the mass of the basketball, I have the initial height of the basketball, I have the final height of the basketball, and I'd like you to figure out the work done by gravity on the basketball. I also have on the right, I have a block that is sliding to the right, and friction is acting on it. I give you the mass of the block, I give you the initial and final positions of the block, and I give you the coefficient of kinetic friction. And so I'd like you to figure out the work that kinetic friction does. So stop the video here and do both of those calculations. See you in a second. So look at this. The work that gravity does is going to be the force of gravity times the distance it acts over times the cosine of the angle in between their tails. You can see that that's going to be a cosine of 180 degrees because if this is the displacement, there's the force. I could have done it on the other basketball too, 180 degrees between their tails. And so the mass is 0.625. The little g, of course, is 9.8. And the height is, difference in height is 1.5, difference between 1 and 2.5. And so that's going to give me a negative 9.19 joules. Now, similar over on the sliding block, I have the coefficient of kinetic friction times the normal force will give me the force, and then times the distance. So that's going to be the coefficient times the normal. There's the force times the distance, and cosine of 180 again. We knew this was going to also be a negative because it's slowing down, and if you put those numbers in, you also have a negative 9.19 joule work. So yeah, obviously I messed around with the numbers beforehand and I made it so that these would come out to the same amount of work, the same amount of negative work. But do you see how they are similar in number, but the outcome is really different? See, the basketball did not become less dangerous. Did it slow down? Yes. Anytime you have negative work, the thing always slows down if that's the only kind of work you have. But you can see that in this elevated position up here at basketball is still dangerous and should be respected. That basketball can fall down. It could do work on anything that's below it. Versus when this block slides over here to the right and it stops, it does not need to be respected. It is not capable of doing anything else. And so we've got a case when gravity does negative work, the energy remains. When the friction does negative work, the energy is turned into heat and it is no longer useful. And so I'm trying to set up a big difference there, that when gravity acts, the ability to do work is not removed, versus when friction acts, I'm not saying it destroys energy because nothing destroys energy, but it removes the ability to do work. That's because fundamentally there are two different kinds of forces, conservative and non-conservative. Now, when we use these words, conservative and non-conservative, we're using them like conservationists. A conservationist wants the environment to stay the way it is, and that's what a conservative force is going to do. It is not going to change the ability to do work of an object. A non-conservative force is going to change it. Sometimes the ability to do work will be changed for the better. Sometimes the ability to do work will be changed for the worse. And so my point is the ability to do work is going to really change when a non-conservative force acts or when a non-conservative force does work, and it's not going to change when a conservative force acts or a conservative force does work. Now, one thing about conservative forces, you know them when you see them, because when conservative forces act, it doesn't matter what path you take. The amount of work will still be the same. And so if we took a basketball and we made it go down this time, if we went straight down, Versus if we took that same basketball and then we shot it up and down, all that really matters is the initial position and the final position. The gravity did the same amount of work in both cases. Compare that with sliding something around with friction. If you slide something forward and back, that does more negative work than just sliding it forward. So when conservative forces act, it doesn't matter what path you take. All that matters is where you started and where you ended. The other thing about a conservative force is if you go a round trip and you come back to the exact same spot. So for instance, say we took this basketball down here and it got down and then we decided to put it back. Well, gravity would have done positive work on the way down, negative work on the way up. It would have done no net work. It wouldn't have done any good. It wouldn't have done any bad. It does no work. Now, those are things that you're going to notice whenever you see conservative forces acting. But how do you know a conservative force? How can you say, oh, that's conservative, oh, that's not? These are ways, but a list would be easier, right? The list of conservative forces is really short. And this is the only conservative force list that there is. Gravitational force, spring force, and then later on in the course, we'll talk about electric force. But for this unit, gravitational force and spring force are going to be the two conservative forces. You see, those are the two forces that have a means to store the energy. So you don't just turn the energy into heat like you do with friction or something else. You have a way to store the energy. Non-conservative forces, you could just say, is anything else, anything outside of those three. Some of these speed the object up, some of these slow the object down. Frictional forces, air resistance, tensions, normal forces, a normal force like you think of a tennis racket hitting a ball, or even lifting your lunch tray, and it's the normal force that lifts the actual food. All of those things either change the ability to do work for the better or change the ability to do work for the worse. They really do change it. They don't conserve it. They're non-conservative. Now, this looks like a lot, but please don't be scared of this. And you're actually going to really like the outcome of this slide. So I am starting off with work is equal to the change in kinetic energy. And you know that when I write work like that, that really means the net work, the sum of all the works. Nobody really puts that sigma there, but I will now just to show my point. Now, the outcome of this is going to be an alternate version of the work energy theorem and you can see it down there in the box and you probably glance at it and say, I don't know if I like that, but I promise you, you will like it a lot in a problem, and it makes a problem a lot simpler. Hey, just two things real quick before we get into that side. Look over here. I want to try to give you a relationship between the change in change in potential energy and the force that goes along with it. That is the change in gravitational potential energy and the work done by gravity, and the change in spring potential energy and the work done by the spring. So look at this kid throwing this ball up in the air. The ball leaves his hand, and then it's under the influence of gravity only. And it's going to go up, 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 and it's going to slow down. Gravity is going to act down all the way, and the displacement is going to be up. So we can see that that's going to be negative work. How much negative work? Well, the force of gravity times the displacement or the height times the cosine of 180 degrees is going to give me negative mgh. Not just that, but the change in potential energy is going to be mgh2. It's going to start off with mgh initial, and it's going to go to mgh final, and the change in gravitational potential energy will be mg delta h. Or in this case, we'll just call it h. Well, my point is, that's the same size, but do you see how that's the opposite sign? That the work from the force of gravity is negative mgh, and the change in gravitational potential energy is positive mgh. And so I'm saying that those two are opposites of each other. Now, I could do a real similar thing with a spring. See, here's a spring, initially relaxed, no energy in it. And then you stretch it out. You pull the thing to the right. The spring, of course, is trying to pull to the left, and so it's doing negative work. And so the amount of energy that you store in a spring is 1/2 kx squared. So you can see that the amount of spring energy has increased. It went from 0 to something more than 0. And so how much? Well, positive 1/2 kx squared. Now, the spring acted negatively that whole time. And you could see that the spring did negative work, and guess how much? Well, half of the k value times the stretch squared, or the average force, which is 1/2 kx times the stretch x. And so I'm trying to say that the change in spring energy is the negative of the work done by the spring. And so all that to say, why am I making an issue of that? Well, the sum of the works is all of the works added together. And that's the non-conservative work and the conservative work. And that covers everything, right? The non-conservative work, there's too many things to list out, but the conservative work in this unit we're only doing as the force of gravity and the force of the spring, and that's all. So now, I just showed you that those works from force of gravity and force of the spring are the opposite of the change in those energies. And so for the work of the force of gravity, I put negative, the change in gravitational potential energy. And for the work of the force of the spring, I put negative change in spring potential energy. They're negatives on the left side, they'll become positive when I put them on the right. And so what you end up with is work non-conservative is equal to the change in kinetic, change in gravitational potential, and change in spring. Now, it looks like there are 4 terms there, but you know that each one of those deltas is actually 2 terms in and of itself, and so there's really 7 terms there. And give this a chance. You at first might look at this and say, oh, I don't like what you're doing there. But if I took each one of these and I made it kinetic energy final minus kinetic energy initial, and gravitational potential final minus gravitational potential initial, and the spring energy, I could make it spring potential energy final minus spring potential initial. You're thinking, oh man, this is getting really nasty. But look, I can take each one of those initials to the left side. They'll all become positive, and I'm going to end up with this that I think you'll like. It's going to be kinetic energy initial plus gravitational potential energy initial plus spring potential energy initial plus any non-conservative work is equal to that same stuff after. So kinetic energy final plus gravitational potential energy final plus spring potential energy final. And yeah, I know that's got 7 terms in it, and it's tough to look at. But I will tell you, a lot of times in problems, and you're going to see that in the examples coming up, that a lot of these end up turning into 0 or adding out, and 2 of them become 0. And this will make a pretty tough problem easier. So I'm going to have you continue this on the video of the conservation of energy examples, and you're going to see how we use this exact same thing. And before we go, where do you go in a room to warm up? Just go to the corner. It's always 90 degrees. See ya.